Hello. So hopefully you've covered this activity and you're just looking for a little bit of help on some of the problems. I'm hoping that I will have made bookmarks in the video so that way you can go to each problem individually. If not, feel free to zoom through and take what you need out of this activity. So for the first one, this is a review from our test question. There are 13 angles to fill up here, and you have to satisfy the 4 angle relationships, okay? So we have linear angles, which linear add up to 180. Vertical angles are across the vertex, which are always going to be the same. And the triangle sum theorem is that the angles inside of a triangle that make up the triangle add up to 180, and then corresponding angles, okay? Corresponding angles are the ones that if you have parallel lines, you can copy and paste. So let's start with that. So I have 2 parallel lines, one there and one over here. And so what that lets us know is that the angles along that line, along those intersections from the 2 parallels, so this intersection and this intersection, because they go along that line, will be the same. And let's use a different color. This intersection and this intersection will also be the same because they have that transversal. So that's the word we would use for that line here. It's called a transversal. Okay, so we have to keep in mind that those angles will be the same. Okay. So if we were given that this is 130, you can make up whatever you want. I would suggest that you make it bigger than 90 because that angle looks like it's bigger than 90, but it can be whatever you want. You just have to put an angle over here that satisfies the side, the linear relationship. Okay, so those two together are a linear pair that make 180 degrees. Okay, I can go up here and we can put whatever we want in here. It looks like they're all pretty close to 90. They're all evenly spaced. I'm going to encourage you not to use 90, okay, because that could be very confusing. Let's say that this one, for instance, is 80. And that would mean that the one over here would also be 80 because those are vertical angles. And then this one would have to be 100 because together those linear pairs have to add up to 100 as we saw earlier. Okay, this is 100. This vertical angle will also have to be 100. Okay. These two make up 150. I'm left with 30 to make that triangle sum work out. Therefore, this one has to be 150. Has to be 150. This has to be 30 because they're vertical. Vertical angles are always the same, and 2 angles that are next to each other will add up to 180 to make a straight line. Okay. We already marked that this angle E over here has to be related to the blue over here. Okay. So something you can do to make things a little bit easier for yourself is extend the lines so you can compare. I'm noticing that I have my sides over there. This looks like the 50 would be the angle down here, right? And this one matches the one down here for E. So this angle has to be E. Let's see if I can make that a little bit clearer for you guys. There. Okay. Because this one over here, the bottom right looks like it's 50. This is the bottom right, so it's also going to be 50. Okay. And then 50 plus 30 is 80, so this angle over here has to be 100. Which is nice because this is the top. If I extend those lines, if I extend this line over here, right, that's the top where 100 is also the top. So it makes sense that those would match. Okay, so it works with the triangle sum theorem, but it also works with those corresponding angles. Everything works out nicely here. Okay, last thing to check or to input in here would be that that has to be 80, either because they're corresponding angles or because they're a linear pair. Okay, all the rules have to work at all times. Okay, it's not sometimes one and sometimes the other. It's always all 4 of them work all the time. All right, so you don't have to use those numbers particularly, but you have to make sure that those relationships are maintained. All right, let's look at the next page. I'm going to delete this. That's from earlier. Okay, so to show the side angle relationship, we need to draw a triangle. I'll draw something like that. Okay. And they're asking us to mark all three sides and all three angles with numbers. Okay, for me, I prefer to start with angles. So this one looks like it's about 90. So we can consider it 90 if you want. These actually look like they're the same, but I'm going to do a little bit different. Let's call this one 25, and then this one over here would have to be 65. And so now we know that the sides have a certain relationship. This side has to be the biggest, this side has to be the smallest, and this one has to be in the middle. Okay, so that's the side angle relationship being played in there. You can start with whatever side you want. If I were to call this biggest side 100, then I would know that this side just has to be smaller than it. Okay, we haven't really talked about the proportions of how much smaller, so don't worry about that. Just make sure it's smaller. So let's just call it 60. Okay, last thing, we know that this one has to be the smallest, so it has to be smaller than 60, but it has to be bigger than when I subtract these two. So it has to be bigger than 40 and smaller than 60. Okay, so something like 50 would work, 45 would work, 35 would not work, okay, because it's too small, because 60 minus the 100 gets us the 40, okay? It has to be bigger than 40 for it to work, so 40 doesn't work either. I'm just going to go back to 50 or 55. Any of those things are fine. They follow the 4 rules. For the angles, right? We weren't even looking at the angles, but the 3 rules we learned last time, which were the side angle relationship, the Pythagorean theorem. You know what? Because of the 90, we should use the Pythagorean theorem. Okay, so if you don't want to have to use the Pythagorean theorem, then do not put a 90 there. Okay, I chose to put a 90 there, so let's make that work. Okay, so that would be 60 squared plus our question mark squared has to equal 100 squared. Okay, next thing I would do, I would subtract that from both sides. 100 squared minus 60 squared is equal to, I'm going to go to a calculator, 100 squared minus 60 squared, it tells me, is 6,400. And then when I square root that, let's see what that is. Oh, that's a nice number. It tells me it's 80. So okay, so what that tells me is that I messed up with my angles. Okay, so I would have to move this angle up here and that angle down here. And now that still works. Okay, if the 90 goes to the biggest, the second biggest is 80, and then the smallest is across from the 25. Okay, so now we've satisfied the side angle relationship, we've satisfied the Pythagorean theorem, and we've also satisfied the triangle inequality theorem, right? So these two, when I subtract them, I get 40. When I add them, I get 160, and this side has to be in between those two. Okay. You do not have to use a 90. If you don't want to have to do the Pythagorean theorem, I'd recommend not using the 90. But knowing that, it is a good practice to practice with the 90. Okay. All right. On to the lesson. So something that I noticed was that all corresponding slopes are congruent. So let's show you how I got to that fact. So I noticed from this point, I go down 2 and over 1. Okay, and then just like in this one, I go down 2 over 1, down 2 over 1, and down 2 over 1, but I do it 3 times instead of just once. Okay, so that's why I say it's 3 times bigger. Over here, I go over to the right 2 and no 0, no going down. And this one, I go to the right 1, 2, 3, 4, 5, 6. I go to the right 3 times. So it's 3 times bigger. You can check that with the last slope, which is to the right 3 and down 2. To the right 3 down 2 is 1. To the right 3 down 2 is 2. To the right 3 and down 2 is 3. So once again, it's 3 times bigger than the blue one. Okay, so something very important to note is slope and angles are very tightly connected. They're just different ways of representing the same concept. Okay. Your job is to just move the slider around and see what happens. Some things to notice is that it gets bigger when it's bigger than 1. It gets smaller when this k thing is smaller than 1. And it's exactly the same when it's equal to 1. Okay, so keep that in because that's actually the big goal for today is understanding when does it get bigger, which is when it's bigger than 1. When does it get smaller, which is when it's less than 1. And when is it the same? When it's exactly 1. Okay. Okay. And then these points, just move it around. This is pretty much to show you that the shapes are always going to be proportional, right? So this has a rise and a run. Let's just do something smaller for counting's sake. Of up to and over 4. This one also has that same slope, but just does it 3 times. So this one shows us that it's 3 times bigger than the blue. And lastly, it lets us move both those things. Okay, so we can change the shape and we can change the scale factor. Okay. So for this dilation thing, you should talk about something about it keeping the same angles or the same slopes or the same shape. Okay. And shapes are defined by the slopes, the related slopes between the sides. Okay. So the idea of slope and angle is very important to state in this explanation. But they can be different sizes. So when you have a dilation, you can dilate to be bigger, to be smaller. You can also just dilate to be the same. It's not. Most people will say it's not dilated, but really it's a scale factor of 1. Okay, so once again, the big picture of today is what scale factor makes a shape bigger, what scale factor makes the shape smaller, and what scale factor makes it stay the same. So those are the big 3 ideas for today. Okay, if we start with a scale factor of 1 on our slider, what happens to the image if we increase the value of k? Okay, if we increase the scale factor, what's going to happen to the image? Hopefully you noticed, I think afterwards, I think you're guessing, and then over here you're trying it. So if we start with 1, oh, it looks like it gets bigger. Okay, so if I increase from 1, it gets bigger. And over here, what if we get smaller? What if we're at 1 and then we get smaller? Like a 0.5 or a 0.3. What do you think is going to happen? Type in your response there. Pause if you are doing this the first time. And then make your guess and then come over and check it, okay? So they've set it up to be k equals 1 and then figure out what happens if you make it smaller. So notice that the red one is getting smaller. Okay, so scale factor. K is known as a scale factor or dilation factor. Write a definition in terms of scale factor. The definition is so good that any other classmate would immediately understand. And keep in mind the 3 questions. What makes it bigger, what makes it smaller, and what makes it the same. Okay, so define scale factor here. How do you make something bigger? How do you make it smaller? How do you make it the same? Yeah, feel free to pause if you need more time. Okay, so images formed by a dilation are frequently referred to as either enlargements or reductions. Okay, if you were asked to perform an enlargement, what would you know about the scale factor? If asked to perform a reduction, what would you know about the scale factor? Okay, so for an enlargement, the scale factor would be, and then do the same thing but for a reduction. The scale factor would be. Okay, so notice we're just trying to home in on the fact that we want you to understand the difference between a growth scale factor and a decay scale factor, and one that would keep it congruent, the same. Okay, so using the coordinate plane, can you figure out what the scale factor is for this dilation? Okay, so things to notice. You don't have to check all three sides to figure out what the scale factor is. If they tell you that they are similar, then automatically we know that all three sides have the same scale factor. So this looks like it's 2. This one's like 4. That means we'd have a scale factor of 2 times bigger. If we go from, it's important to say where we're going from the red to blue has a scale factor of 2. So we're multiplying by 2 in that case. Okay, when we're talking about the direction and how big we're getting. Okay, and you can double check it by looking at a different distance. This one is 4, and this one should be 8. 1, 2, 3, 4, 5, 6, 7, 8. Yes, so it's twice the size. Okay. Cool. And then so this is a way you could check without me being here, letting you know. Hopefully you're doing this as a review rather than listening to me talk you through it and just copying down what I say, because you are not getting what you need to out of this if you are just copying what I say. Okay, so next one, side lengths. If you had a triangle with side lengths of 2, 4, and 5, and it dilated with a scale factor of 2.5, what would the side lengths of the new image be, the resulting image? Okay, so 2.5 times bigger. So that means double plus half more. Okay, so the 2 turns into a 5. So a 4 plus 1, which equals 5. The 4 would turn into, if I double that, that's an 8. And then half of 4 is 2, so that'd be a 10. And then the 5 doubles, turning into a 10, and then half of that is a 2.5. So that would give us 12.5 for our distance. That's my thought process on multiplying by 2.5 as a scale factor. Right, you double, and then you get half of a little bit more. Okay. If you had a rectangle with side length 12 and 4, and dilated it with a scale factor of half, what would that be? So we have a rectangle. Rectangles have 2 equal sides, and we're dilating with a scale factor of a half. So the 12 turns into half of 12, which is 6. And then the 4 turns into half of 4, which is 2. When a pre-image is dilated, can the resulting image be congruent to the original? Okay, once again, if you have not filled this out yourself, you can press pause and think about it and explain. But if you have, then I just want to remind you that a scale factor of 1 gets us the original image. It makes it congruent. Okay, so very important to know is that a scale factor of 1 means that it's congruent. Here's a picture of the dilation described on the previous slide. Did the dilation change? Oh, this is out of order. I gotta fix that. Did dilation change the side lengths, the angle measures, both or neither? So something to notice here are the angles stayed the same and the side lengths did change. Okay, it looks like the side lengths doubled, but the angles are still rectangular, which means 90 degrees. Okay, so the pre-image is in blue, and then that means before, and then the resulting image is in red. So it went from the blue to the red. That's where they're telling you the direction. Okay, describe the dilation that must have taken place with an enlargement or a reduction. Be sure to include either the center of dilation and the scale factor in your description. So we haven't talked about center of dilation. I'm okay with you ignoring that, but I will talk about it. That is definitely not one of our requirements for passing this unit. But this idea of scale factor definitely is. So if we start at the blue, looks like the blue is 3 times bigger than the red. So the scale factor from blue to red appears to be 1/3. Okay, so if it's 3 times bigger, going the other way, it's 1/3 of the original one. Okay. The center of dilation means from what point are we getting bigger and smaller? Okay, so that's what they mean by the center of dilation. From where are we getting bigger or smaller? On a lot of the examples we saw before, we were getting bigger and smaller from the origin. Okay, we'll see if I can find a point like that. Yeah, notice from the origin we were 2, and then for this picture we're in origin, from the origin we're 4, so it got bigger that way. Likewise, this is from the origin up 1, so this became an up 2, it doubled. Okay, this was up 5, and that distance doubled, so that means our origin is the center of dilation for that one. But in the problem that we're doing, the center of dilation, once again, this is not required for everyone. This is just if you're going for the A, then the center of dilation would be 2, 2. It's actually that spot right there, because that spot didn't move at all. But this one was at a 6, and it went down to a 3. This one was at a 11, and it went down to a 5. Okay, so it got half of that distance. And really, it wasn't the 5 that's important. It's really that it went how far away from it. It was 6 away, and now it's 2 away. This one is, how many away is that? From 2 to 11, 9, and then we went to a 3. Okay, so it was a third. So it's not really the 11 that's important in that case. It's the distance from the center of dilation up to the corner of the shape. Similar. Instead of referring to these triangles as congruent, these triangles are best described as similar. What do you think the geometric term similar means? Okay. So similarity, we're just calling these similar because they do stay the same shape. They have the same slopes. But notice the sizes change with a scale factor that's consistent. All 3 sides have a scale factor of 1/3, right? You got a third of that, a third of that, and a third of that, and it shrunk. Okay, so a consistent scale factor is important to similarity. For all the sides, consistent scale factor for all the sides. And the other thing was that all angles, or the slopes, are congruent. So those are the 2 big things for similarity that I'm hoping that you're getting from this exercise. Drag the vertices so that the red triangle is the dilation of the blue one with a scale factor of 2. So we're going to go twice as far. So we want to go 4 to the right. That means it has to be there. This one was 3, so we want to go 6. And then this one was 7, so I want to go to 14. Way up there. Oh, it's not letting me get up there. There we go. Okay, so that would be a scale factor of 2. Everything's twice as far. So it was 3 and now it's 6. It was 1 and now it's 2. It was 4 and now it's 8. It was 1 and now it's 2, and so on. Okay, and we can tell that because it's along those lines, which is nice. Makes it quicker if we have those lines drawn.